Okay, so welcome. Glad that you're here. I can't do this tomorrow night. My son has sports and things, so I'm doing it tonight. Exam one is Thursday in your normal quiz section. Um, posted, so this is my general list, and so I'm going to say a few things here in terms of topics. So exam one does not include 13.4. I leave it on here just so I don't forget to say that, which means we don't have the principal unit normal. We don't have velocity, acceleration, and speed. And we don't have the tangential and normal component of acceleration. Those are not going to be on this test. I'm sure we'll encounter those as we go through old exams. The first page will be about things of this sort. The second page will be about lines and planes. And the third and fourth pages will be on the other things. I think I said in my post, page three, page four. So if I were a student, I'd want to make sure I knew the key formulas, the key dot product, cross product, projection, distance, sphere formulas. I'd want to make sure I knew how to find the equation of lines and planes and was comfortable with a few different scenarios. Um, and then be able to compute the new stuff we've been playing with. So I could go through and give some of those facts. I may do some of that in class, but I think our best use of our time is to try to do some questions. But I'm going to show you a couple things because no matter what we do here, we can't usually get to everyone's questions. I'm still stalling while you collect your questions. So if you have a particular topic you're worried about, grab old exams and find me ones to put in the chat in just a moment. Okay, so while we're thinking about that, I wanted to show one other thing. So here's our Canvas page. First off, on my materials page, there's a few things that might interest you if you weren't aware of them. The big one is my exam archive. So let me put this in the chat just in case. There's the exam archive. So there's a department exam archive as well, but my exam archive has a series of short videos on topics. So if you need a review of vectors, kind of page one stuff, lines and planes, surface names, and curves. Um, there's several things there. If you want old exams with solutions, some in recent years I've been making videos by page. So that's one collection of review material. Thank you. And then another spot is the test preps I used last year were more old exam questions. So if you just needed practice with a certain thing, you could go back here and click on whichever thing you need practice with. So there's plenty of practice, but your job is to collect what you have. Please also ask me questions on the discussion board if you haven't been going there. Um, I have study tips, a few other things. So right now, if I were you, I'd want to dig into that exam archive and start to get myself familiar with where I'm stuck so I can know what questions to ask. Okay, the only other thing, before we totally open it up, is I do have on my channel here, I have a playlist of lots of stuff. More, now it's gotten too big, but in there is Calculus 3 in small bites is a lot of short videos on things that have to do with Calculus 3 that students struggle with. So that might be helpful anyways. And Math 126 exam prep has a bunch of videos where I go through exams and things like that. But I think it's better to go through my materials page where I've organized it. All right. Logistical questions. I might have to let my cat out of this room in a moment. So what I'd like to do is follow, this is just to get a small collection. I'm going to follow Aria's lead. So they wrote me a direct message, but you're welcome to message with everyone. So someone has already said winter 24 3B. And then there's a question spring. So what I like to do just to get us started is to get a little sampling of what questions. So you can put it in the chat and I'll start writing. What does it mean conceptually? I'm having a hard time trying to imagine, visualize. Okay, so this is a conceptual question. Other ones, so thank you, Winter 24 4B. We may not do all of these, but I think it's helpful to see what questions other people have. We'll get a sampling. Thank you, Owen. Anybody else want to put a few on our list, our queue? Those sound like chapter 13 questions, possibly. Feel free to put more in the chat here. Here we go. So we have spring 13, question 2B. Lovely. And then I'm just going to do a few more. Once I kind of fill up the space, I'll stop. We'll take a look and then we'll dive in. I found this to work reasonably well. Celine said 25. Gotcha. I see the correction. Why is my eraser so big? 25. Okay. Will we be expected to draw 3D shapes? Someone is saying, no, you won't be expected to draw 3D shapes. But it is sometimes helpful in terms of visualizing. Projection. So there's a general comment about projections. Lovely. Can we discuss projection? Someone else is asking that. Okay, so we have a little bit of a sampling of things. Um, okay, here's another one. I see it coming in. I'm going to cut it off in just a second, but then you can ask more. We have another comment on projections. Okay, you can ask more questions in just a moment. I'm just going to pause it here and take a look at what we have. Spring 24, lovely. Question 1. Okay, so let's kind of peek here. So we have a couple questions from spring 2019, winter 24. So let's go to winter 24, and we are going to do what I like to do. So we're going to open up the exam, and then I am going to tour through the exam, making sure we stop at those problems. I think that's a pretty helpful way for us to work here. Gabriel, good. Okay, so here we go. We're gonna go winter 24 open. That's a little too small. Uh, here it zooms in. I know you can't see it quite yet. I'll get it there. Yeah, this is the same OneNote. Maybe I can try it right here, but it's the same OneNote as my lecture OneNote. Share entire notebook. Copy link. It won't let me do this. I'm trying right now to share with people at UW. Apply, copy link. Everyone. I will try here real quick. There you go, Gabriel. We can try, but if it doesn't work, we'll just take what we have here. Okay, so we're looking at the winter 2024 exam. Um, so what I'm going to do is pretend I'm a student here. I'm going to make sure we look at a couple questions. Great. Um, so let's look, and I'm just going to remind myself real quick. The questions were 4, 3, and 4. Okay. So it's good. We could stop and probably talk about every single question, but there's that first one. Find and simplify an equation for the surface consisting of all points such that the distance from here to here is the same as the distance from here to the XY plane, and then name the surface. That's actually more of a 12-6 question. So if I was going to ask that, it'd be on page 3. But it's good to sort of stop. If I was a student, I'd keep a little notebook of, okay, I don't know how to start that one. And some of my studying would be collecting where I'm stuck. Do we have a plan here? Find the area of the triangle formed by those 3 points. What we're looking for when we're doing this quick studying, when we're touring, is anytime we pause, because however long we pause and think about it, it's going to be worse during the test. So my question is, do you know how to start? I'm going to adjust so I can see myself. Somebody in the chat, just tell me what's the first thing you're going to do here? Yeah, you're going to get the vectors. You're going to do A, B, and that's going to be subtraction. So this is the sort of stuff I'd be wanting to do if I was a student, is just honing my recognition, my start, getting some comfort. Hopefully I did my subtraction right, and then doing a cross product. Yep, you're going to do the cross product, get the magnitude, do 1/2, and you'll actually do it. But right now, nobody asked that question in particular. As I go through this, you might get ideas of questions you want to ask. The questions that were asked were on problems 3 and 4. Then there's a question that says find the equation of the plane. Make this a little bigger. Oops, that messed me up. Okay, there we go. Um, find the point. Okay, that's something to do with projection. So we could come back to that. Okay, then there's a question about find the equation of the plane. So this is what you're trying to do, is say, would I have any idea or would I just be stuck? And so we're looking for those problems where we're stuck right out of the gate. Find equation for the line of intersection. Okay, nobody asked those questions, but we can come back. So somebody asked a question about problem 3. So right now we're on winter 24, problem 3. Okay, so that's, if you're new, that's kind of how I do this, is I look at an exam, we take a little tour, try to grab a few things, and then I try to get to where people's questions are. Somebody's asking about recognizing and starting problems. I mean, this is one way to get better at it. Uh, yeah, so let's keep going, and before we get to general advice. But the other way is to kind of be really comfortable with the homework. But let's go here. Consider this curve given by this. And the other thing you can do in terms of recognizing problems is, as you're doing this sort of studying and you didn't know how to recognize it, make a note of the next time I see this, I do that. If you keep doing that, you'll quickly get through all the types of problems. That's what we're really trying to do when we're studying, in my mind. Okay, find the equation of the tangent line at this point and give the point of intersection. So this is two different questions. But the moment I see this, I know what to do. So we want to be ready for this. How do we find the tangent line? This was sort of a thing from lecture. We need some. Okay. So you're going to take the derivative. Definitely, if the word tangent is in a problem, you will take the derivative. We are trying to find a line. So this would definitely be my note sheet of it, and you would encounter this if you look at any of my old tests. So you definitely would have this in your note sheet of, all right, in the homework we had to find a tangent line, in the old exams, and the things I need to do are what? And this is what I'm trying to get you to do. So we need to put a point here. In this case, they give us, so it's at whatever time they're talking about, and we need the direction. And that's what our prime is. Okay, so that's what we're trying to do, is check off these ideas. So immediately when I see this problem, I go, but wait, they didn't tell me the time. And this kind of hits on something I mentioned today in lecture, which is really before you even start the problem, it would be nice to know the corresponding time. So how do you find that? Yeah. So they told me, so if you're having trouble with this is X, this is Y, this is Z. And they're telling me this is 5, this is negative. negative 6. This is a negative 3t is negative 6. And oh, it said my internet's unstable. If I lose you, I'll immediately hook it back up. I don't usually see that. But anyways, what did you get for t? Everyone blow up the chat. T equals what? 2. Great. Okay, so that's our first thing. So somewhere in your note sheet, you go, okay, somewhere on the test, they're going to give me a point, and I'm going to need to find t, and I want to do that. Okay. You'll notice in my solutions that I often don't like to use a t here because it confuses me to have too many t's in the problem. But if you use a t, that's fine. Okay, so there's our first little thing, is they gave me x, y, and z. Make a note to yourself so that you know that, all right, if this happens, I can solve for t. The rest of the problem is fairly computational. Okay, so we need to figure out R1 of 2, which we already know, they told us, is 5, negative 6, 8. 5, negative 6, 8. And we need the direction, which I haven't done yet, the derivative. So the derivative is 2, negative 3, 3t squared minus 2t. And in particular, I want it at 2. So one of the most common mistakes I see is people will just put this in here. So that's why we needed that 2. What do I get if I put a 2 in here? 12 minus 4, 8. And all of these exams have solutions in the archive. Definitely let me know if my answer doesn't match or if I do something wrong. That's the tangent line. Okay, so how I would think about studying is, all right, I have that problem now. I've got it. If somebody says find the tangent line, I know what to do. That's a personal thing. As you are a college student, you learn to find when do I know something. Um, so I know that now. That's why we want to get. It's not wrong to keep it as a T. So it is perfectly fine to keep this as a T. I just know that the moment I do that, I start to get confused at what goes with this. This T goes with the line. This T goes with the curve. As long as I can keep straight which came from where, then I'm fine. But as soon as I start mixing things up, then I'm in trouble. Okay, the next part of the question, I was focusing on the tangent line part. So we have not finished the question. The next part of the question is fairly quick though. And give the point of intersection of the line in the plane. So that's a separate question. So how do we find the intersection of a line in a plane? We combine. That's actually a really quick question. So let's finish this problem. We're going to replace x with 5 plus 2t. We're going to replace y with negative 6 minus 3t. We're going to replace z. And if you need me to color code here so you can see what I'm doing, I replaced y here. I think I have the wrong eraser. There we go. That's better. Aha. There we go. Okay. So, and then I replace this went here. And lastly, we're going to do this, goes here. That's the combining step. Okay, so this is going to be 8 plus 8t equals 42. Solve that and we're done. So let's see, we get 5 plus 2t minus 6 minus 3t plus 8 plus 8t is 42. Put those three things together, that's 7t equals, put these things together, minus 1, that's 7. Subtracting 7 from, I'll show what I'm doing. Subtracting 7 from 42 gives me 35. And t is what? 5. Now, we're immediately going to answer a question here, which is where in the world do we plug that t in? Plug it into what, though? The tangent line. So I'm pretty sure when I wrote this question, it was partially for this reason. This is why I tend to get confused and why I, when I do this problem, put a U here and solve and get U, because when I do that, it's easy for me to see where I'm supposed to plug it in. Because we used a T, it was hard for me to know at the end, where did this come from again? So that was my point of that. But you can use a T as long as you don't lose track. So it's going to be 5 plus 2 times 5. So it's going to be 15. It's going to be negative 6 minus 15. So negative 21. Don't trust me. And 48. Can anybody verify that? Thumbs up. Thank you. It would be the same for the tangent line and the plane. It would not be the same if we plugged in t equals 5 up here. Because t equals 5 on the curve could be something totally different. Visually, what's happening is we have a curve, we have a plane, we have a tangent line that hits. Just because this hits at 5 doesn't mean this hits at 5. Does that make sense, Ketki? Yeah. So that's the confusion. Um, and I'm trying to reply to, for you, I'm saying something weird. It's okay. So that's it. We got to practice intersection. We got to do a tangent line. So you sort of chunk away what you can. All right, let's keep going here. Find the angle of intersection. I believe somebody was asking about that. Find the angle of intersection to the nearest degree of the first curve and this other curve. Okay, so I need that first curve again. I'm going to do something we can't do on the test, which is screenshot and paste. Uh, you'd be able to see the whole thing on the test, though. Okay, so there's curve one. Oh, it's not letting me. See, I guess I can't do it. Okay, so we're going to do R1 of t is 2t plus 1, negative 3t, t cubed minus t squared plus 4. All right. Do we want to see this question? Anyone want to see angle of intersection? Yes, great. So this is, again, two different things. This was the question we ended class with in 13.2. This is, I don't always ask this, but it is pretty common if you look at my old exams. So this is yet another thing of, okay, I can do a tangent line. Now could I do an angle of intersection? First, I need to find the intersection. So I need to find when the x's are the same, the y's are the same, and the z's are the same. Okay. So if you're someone who needs a step by step, or this is the sort of thing you would do if this sort of question bugged you, is find the times when they intersect. So find when this x equals the other x, and find when the first y equals the other y, and find when the first z, that's supposed to be a u, equals the other z. And when I put these little question marks, they're not essential. You don't have to put those. I put them there to say, hey, I'm trying to solve something here. It's not what the original thing was. Okay, so those are my three equations I need to combine. The reason we're doing that is so that we can know the t and the u when they meet. So go ahead and do that really quickly. Whoever's fast, find me t and find me u and verify. So in the chat, let's blow it up. T equals blank, u equals blank. I'm just seeing what pops up here. Okay. Yep. So this one works out kind of nice in the fact that we can immediately see that this is t equals 2, and we can plug that in here and verify that 4 plus u equals, I guess that's 5. So u is 1. But it's good to kind of keep track. At this point, I've only combined the first two equations. Now I'm going to check the third. When I put a 2 here and a 1 here, I hope I get the same. On the left, I get 4 times the square root of 4, which is 8. On the right, I get 8 minus 4 plus 4, which is also 8. Okay, so let's kind of summarize where we're at. So I checked. Just this, well, the question didn't ask this, but I'm going to put it over here. The point of intersection is, let's see, something -6. So 5, -6, 8. Question didn't ask for that. And the times when they occur are this. So there's another part to this question, which is the question's asking for the angle of intersection. So step 2, angle of intersection. How did I get the point of intersection? Good question. I took this and plugged it in here, and I took this and I plugged it in here to verify I get the same thing. So notice when you plug in a 1 here, you get 5, -6, and then 4 times the square root of 4, which is 8. Does that make sense? Somebody's asked me a private message on this. Yep. Okay. So the other thing we need, and so the big idea when we were talking about this was when we talk about the angle of intersection, this is the conceptual idea here. We mean this angle. We do not mean the angle between their locations. The location is just this vector. It's the same for both. We mean the angle between their directions. Their directions are given by the derivatives. Yep, so you have to find the tangent vector. The reason we found the intersection first is because we needed to know when it happens. But now we need the derivatives. So this problem forces you to use the position and the directions. That's why it's kind of a good exam question. It forces you to keep these things straight, and requires you know both and what they represent. Okay, so we need the angle between the tangents. And now we know it's when t is 2 and when u is 1. So step 1 was necessary to get the t and the u. Let's get rid of this. Okay, so now we'll finish the problem and we're there. So we're going to get the derivative of the first is 2 -3, 3t squared minus 2t. Somebody's asking, how did I get these values? I got these values by combining the three equations. So when are the x's the same? When are the y's the same? When are the z's the same? For these two curves that they were asking about. And the way we do that, so first to Adam's question. Does that answer your question, Adam? So I solved this and got t equals 2. I decided to substitute that into the first equation because that looked easier for me. And then I solved for u. Does that answer your question, Adam?
Yeah, thank you.
Yep, good. Um, Sophia is saying, why are we not finding the angle between their locations? So if you were to do their locations, if you were to do R2 of 1 and R1 of 2, they both would be the exact same locations. And what would the angle between them be? It would be zero. This question, if you were all doing the angle between the positions, it will always be zero when they intersect. That's not what so let me do a little 2D picture. We do not want the angle between this and this for two different curves. We want the angle of intersection means the angle between the directions they're going. That's what this means. So some of it may be just understanding this definition, but angle of intersection means the angle between the tangents. Okay. So anyways, I need this derivative. I need the other derivative. The other derivative is 1, 0. Oh, and then we have to remember a derivative. The derivative of 4 square root of, that's the hardest derivative in here. So that's the same as 4u squared plus 3 to the 1 half. So it's going to be 1 half times 4u squared plus 3 to the negative 1 half times, I'm going to leave some space here to see if anyone's still awake. What goes right here? Yeah, it's a chain rule. Hey, a few of you are awake. Okay, great. Um, how do I finish the problem? I want the angle between those tangents when I plug in a 2 here and a 1 here. And let's see, if I plug in a 2 to the first one, I get 2, negative 3, 12 minus 4, so 8. And the second one, when I plug in a 1 here, is 1 comma 0 comma whatever in the world this is, which is 4 over the square root of 4. I think it's 2 because this right here is, yeah, those 2's cancel. 4, 4 to the negative 1 half. Yep, it's 2. You'll say something in the chat if those vectors are wrong. And then we finish the problem by finding the angle between them. So a reminder of our 10 star fact. If I have two vectors, A and B, we can say the magnitude, we can say the dot product of A dotted with B is the magnitude of A, magnitude of B cosine of theta. So theta is arc cosine of the dot product, which we can do quickly, 2, 0, 16, divided by their magnitudes. Square root 4 plus 9 plus 64, square root 1 plus 4. So this is arc cosine of 18, 68 and 9, 77. So square root of 77, square root of 5. Does anybody want to tell me in the chat what they got when they calculated that? 23? 23 point something? Yeah. It says to the nearest degree. If it was 23.5, it would be 24. Maybe it rounded to that. Yeah, the only comment is the question did ask nearest degree. So there could be some credit for that. So this is a question that I would say sometimes people are like, boy, that's a lot of steps. It is, but you'll see it's on quite a few old exams. So to me, as a student, I'd be like, I can hammer this question out. I would be ready for it. I'd be like, all right, angle of intersection, I know what to do. It's something I can prepare for. So I'm just trying to give you that little bit of perspective of find the intersection, find the derivatives, do the angle. If it says a particular answer, I would say most of the, if I was grading this question, let me look here. This is 12. Let's say this was 6 points. My rubric probably would be something like, did they find the intersection correctly? Maybe that's 2 points. Did they know that they needed to do tangent vectors? Maybe that's 2 points. Did they know the dot product fact and do their final computation? That's 2 points. So formatting usually is never more than one, maybe a half, maybe not at all. So anyways, okay. We can do homework in a moment, but I want to continue going through this. So somebody's asking about do we have to plug cosine inverse into our calculator for the angle? In this case, I asked it on this test. So you would need to. Okay, so somebody's asking about question 4 as well. Correct? Correct? I'm trying to kind of manage everyone's desires here. I'm going to stay on for a while. We're going to go past 8:30. Um, but I know that I'm not always doing the question everyone wants. So we did that one. And right now, a couple people asked about question 4. So since I have and we also previewed a little bit of the rest of the exam. This is in the chat, so if you joined later, I can share it. Let me share it again. Yeah, so if you join the video, the Zoom after the beginning, you can't see earlier in the chat. But earlier in the chat, I put this link in here, so I'll put it in again. Here it comes. Boom. And one more thing. If you aren't there, just a moment. I'll get back to our here exam archive. Exam archive. Okay. So let's go here. So like I said, I like to stick in one spot. So the question here is winter 24. And I think the question specifically was about B. So this question is like there was one question in the 13-2 homework that was like this. So we can talk about that in just a moment. This question is related to the things we were just finishing today in class. Is that okay? So these are very different things, these two questions. Um, do we want to talk about one of those? I know a few people are asking. Is anyone still here that wants to do those? A? Okay, let's talk about A briefly. Um, we will do a part of the reason this looks different is just simply that I didn't do an example in lecture and you just had one in homework. We will do more things like this in 13.4, but I think we can do this one. So what this question is saying is someone has taken the derivative and they got this function, and this function. And then they're doing this weird thing of giving us some initial information. This is like 3 mini calculus 2 problems. So they're telling you the derivative of x. I'll try to make it look, how can I make this look as familiar as possible? The derivative of x is this, and x of 0 is 1. So let's do a quick review. If someone gives you the derivative of a function and they give you an initial value, which is what they're giving you here, x of 0 is 1, x prime of t is this. Remind me how we go backwards. So go ahead and write down what the antiderivative of this is. This means that x of t is this, yeah, plus a constant. The way we find the constant is we plug in our initial information. 0, 1. When we do that, I think I get e to the 0 is 1. So I get 1 plus c is 1, which means c is 0. And we're done with the first component. E to the 2t plus 0. So ultimately, I didn't put a lot of emphasis here because we'll do more of this in 13.4, but that's what this was in the homework was they're giving you three different derivatives. So then they say y prime is secant squared, which looks scary. You're like, do I need to know my secant derivatives? But if you remember, secant squared is something we really like. Because this somebody's asking, could I ask this? The way this is asked, I could ask it on our test because it's directly like this 13.2 homework question, and that anything in the homework is fair game. That's ultimately your guide is if I ask the exact, some of the homework questions are too long for a test, but if I ask something that's worded exactly the same as something in the homework, you want to be ready for it. So it is good to add that to your studying of opening up the homework and being like, which one of these would I not be able to start? Um, because I definitely, when I write the test, pull from the homework. So that what's what makes this fair game. Yes, I didn't emphasize it as much. This was probably a quarter where we had more time, but if I could ask some more basic one. Anyways, this means that y of t is where did secant squared come from? It's one of our things we like. It's tangent plus c. Sometimes because the constants I don't want to assume it's the same constant. I put a little C2. And then we do the same thing. When you plug in a 0, you get a 2. So when I plug in a 0 here, I get a 2. And that means C2 is 2. So this is tangent plus 2. And then lastly, Z prime is this. And Z of 0 is 3. Why are you plugging in 0? Good question, because this right here is 0. So this is telling you that when you plug in 0 to your x, you get 1. When you plug in 0 to your y, you get 2. And when you plug in 0 to your z, you get 3. So part of this is getting used to the notation as well. Okay, so the hardest question here is this one. How do we do an antiderivative of this? Yeah, substitution. I was mean this square. Okay, u is t squared, du is 2t dt. Pick your favorite way of doing that. You can solve for dt. You can rearrange. It's going to ultimately be 1/2 the integral of sine of u du. And then sine comes from negative cosine. So z is going to be negative 1/2. Why did I write that so poorly? Negative 1/2 cosine of t squared plus a constant. And when I plug in 0, I need to get 3. So when I plug in 0, I need to get 3. So negative 1/2 plus C3 is 3. So C3 is 3.5. So this is negative 1/2 cosine of t squared. So ultimately, it's good for us to talk about that. I probably would have a shorter version of that if that was on my test, and we'll talk more about that in 13.4. But it isn't bad for us to see this as we're studying, um, and kind of see what's different. Okay, but I don't want to get bogged down in reviewing integration. That will come more later. Okay, let's talk about the other one. There will be a time we talk about integration a lot, in chapter 15. Any lingering questions on that part? So it was three antiderivatives. The challenge was this. Okay, let's go forward. Are we okay? Can we go to the next part? thumbs up or something. So about points here, each of these would be worth doing antiderivatives and finding the constants would be worth points. This is just me estimating what it might have been. So let's say you messed up on this antiderivative, but you used the constants correctly. That's probably 5 out of 6. So, when I wrote that question, I was like, okay, there's one slightly harder derivative. The biggest problem here is that if it suddenly eats up a lot of a student's time. Um, but anyways, if you're worried about credit, that's it. Okay. Um, let's move on to the next part. Find the value of x at which this has maximum curvature. So in one of my classes, we spent a little more time on this. But the question is, if you are driving a car along this curve and we're looking down from above, when are you turning the steering wheel the fastest? It's actually somewhere in here when e to the x is bendiest. When you get out here, it's not very bendy. And when you get way out here, it's not very bendy, actually. There's somewhere in between. So when is the e to the x function the bendiest? It's my casual way of saying it. But the whole point is we gave a formula for this today. So this question is saying, look on your note sheet, know that this is f double prime of x divided by 1 plus f prime of x squared to the 3/2. So your job in this problem is to say, okay, curvature, there's our formula for curvature, but I need to know what f prime of x is and f double prime of x is. That wasn't so bad. One nice thing about e to the x as well is it's always positive, so these absolute values aren't really necessary. So we have it. The curvature for the e to the x function is e to the x over 1 plus e to the x squared. So I'm just going to write e to the 2x. Done. So that's something new. That's the new toy we're playing with. The question's asking me, so the calculus challenge here is how do you find when something is maximum? This is a whole new function. If you were to graph it, it actually looks something like this. How do I find this peak that lines up with when the curvature is maximum? Yeah, so this is one of these questions that looks worse than it is. We need to take the derivative and set it equal 0. This was the last question on this test. It was like the challenge question. But the question is, can you take the derivative of this and then find when it's equal to 0? And I know that looks bad, but if you just, this is one of these questions that if you just write it down, it will work. Meaning, okay, I'm about to do my quotient rule. Denominator times derivative of the numerator minus numerator derivative of the denominator all over the denominator squared. That's what I always think of when I'm doing the quotient rule. Here's the denominator. When I teach this in Calculus 1, I say you can put all the stuff in that requires no thought. And if I was doing this problem, I wouldn't even write the denominator because I know that I'm about to find when this equals 0. So putting the denominator here is not necessary. But I've left off two things. So to see if anybody is still awake, tell me what goes here where this star is. It's the derivative of e to the x, which is e to the x. Okay, harder question. Don't put this in the chat because I don't know how you're going to type it in. Think about what goes here. This was tough. This was a tough challenge to finish this problem. Now, there was, in terms of grading, I'm sure that I gave credit for writing this down and attempting to do this. The challenge was finishing. Okay, so I need the derivative of the denominator, which is going to be 3 halves, 1 plus e to the 2x to the 1 half times the derivative of the inside there. So it's 2 e to the 2x. Ah, you did it. You put it successfully. And you also canceled the 2. Uh, great. Okay. So someone successfully typed it in the chat. All right. So there we go. Um, somebody else. Oh, no, you got an extra 2. Um, so we need to know when this is 0. So I have learned through practice. So this is the challenge. Like I said, this was the challenge question. I've learned through practice that I'm not scared of that because I'm going to multiply both sides by the denominator and then I'm going to clean up the numerator and the answer will be there. So it's unfortunately, this is a tough question. I must have winter 24, um, 3e to the 3x. But we can solve that. We can actually factor it or we could move things to the side. Did I hate that class? I don't know. Uh, just remember this because usually when I give a test, people are like, that test was way harder than the archive. So remember this question. The archive doesn't always have. So, anyways, we can do some simplifying. We can divide both sides by this, and it makes this a 1. We can divide both sides by e to the x, and we get 3 e to the 2x. Oh, wow. What just happened? It's way nicer than I thought. I normally don't ask a big algebra question like this. I just thought it was interesting to see when is e to the x bendiest. Um, it's when the log of a half is equal to 2x. It's 1 half the log of a half. Or if you know your log rules, it's negative 1 half log of 2. I did all that quickly at the end. I'm going to make sure I didn't do something silly. I divided, I subtracted negative 1 half log of 2. Is it negative? I don't remember it being negative. I guess you can verify. The curvature for e to the x. Yeah, where I divided both, I did a bunch of little things there. I divided both sides by e to the x. That made this e to the 2x. I divided both sides by the square root. That made this to the 1. Um, all right, I feel like I want to graph it, but I'm not going to. I do want to remind everyone that can we see this? Yes. If I slough over something, you can click here, you can go here and see my full solutions for this whole thing. So if anything on that exam bugged you, like how did we translate? How do we find that area? You can find some things and then ask me particular questions. We did this one. Hopefully that matches. We did this one. We did that one. It is negative 1 half log of 2. Okay. Okay, so let's do a little. So we did kind of a big tour of winter 2024. And I think we hit um, tangent vectors, tangent line, curvature, intersection of a curve and a surface. We did have intersection of two curves. I think we also did something with angles. Good. We'll see, Sophia. Let's keep it rolling, though. So there's a couple questions here on Spring 19, maybe that would be interesting to look at since there's two different questions there. So I think I'm going to go there next. And maybe Spring 19 question one, because we haven't really hit on these things. And then we're missing a big topic. Somewhere before the end of today, um, we're going to do this. Dikshita, that's the quotient rule, is where that came from. So briefly before we completely leave, because there's a question here. Um, this was the curvature. The challenge of this question was that it was asking when the derivative of this is zero. Because generally the way I teach derivatives, and we'll have a big lesson on this when we get to chapter 14, and I'll review. But if you see a mess of symbols all together, so here's the 2-second review of derivatives. But if you see something like this, where it's separate terms, then we got no problem. We take the derivative, we take the derivative. That's the sum and coefficient rule. The moment one of the terms has a mixture of things in it, then you think product, quotient, or chain. Here it would be the product rule. So the moment I see this and I need to take the derivative, I go, oh, that's a big fraction, n over d. This is the quotient rule. That's how I write it. Denominator times derivative of the numerator minus numerator derivative of the denominator all over the denominator squared. So we'll review that in a bit. Yeah, yeah, okay. So let's look at spring 2019. Ooh, I have some writing on there from the last time I taught this course. Spring 2019. Ooh, we have an owl in our neighborhood. I just heard it outside. Um, let's do this. So question one. So I'm glad this is not, here we go. So this is something we're pretty certain is coming. So this is spring 2019. This will probably be, if I was going to ask this on our test, it would be on page 2. Find parametric equations for the line of intersection of the two planes. This is another one of these things that I would like have at the ready. So if we sort of summarize a few things already, I was just going to make a note. We now know, hopefully, we see a tangent line question, we got it. I'm hoping at this point. Um, we see an angle of intersection. Hopefully we have it. And if you look through old exams, that's a couple big things already. So that's how I think about as I'm studying. Do I have a clear plan and am I confident? Okay, so when I look at this, when I need to find the line of intersection, is that something I know? That's a big topic that you're going to see on lots of old tests. Even if you just flipped through a few tests quickly, you'd see it a few times. You'd be like, okay, I definitely that needs to be something I know how to do, or I need to have a plan. That's one way you go through the exam a little more efficiently, is already have looked through several old exams quickly and said, okay, I know how to start this. I know how to start that. Okay. So this one, I know the moment I see it where I'm going to start. So I'll take a moment while you think about what you're going to do. If you have a hesitation at all, then that's something you need to add to your note sheet of line of intersection. What do I do? And there's actually multiple solutions. Somebody on the discussion board was asking about alternative solution to a particular homework question, and then somebody else was asking about an alternative solution to exam. So I made a video where I did this type of problem in 3 different ways. And then I showed which I think is the best. And in my opinion, I do all questions that have to do with finding a line the same way. I try to find 2 points. Because if we can find 2 points, then we're done. Put one of the points here, find the vector PQ, done. You can multiply the equation. My immediate focus is to reduce the number of variables and then find 2 points. There are multiple ways to reduce the number of variables. The standard way is to solve for one and shove it in the other. Another way is to subtract them side by side. So if you want to be, when I look at this, probably the most efficient way to put these two things together is to subtract them side by side. But that's kind of a trick because I saw the two x's here and I saw that that'll go away. If that's confusing to you or you've never seen that before, then you just pick a variable and solve for it. Like you could solve for y and you get y equals 4. Let me be careful. Add the y to the other side. Y equals 2x plus 8z minus 14. And then you shove that in the other one. So that's one way to get rid of a variable. Another way is to add or subtract side by side. So to me, that's the first step. The first step when I see this problem is I am going to combine equations. That's my first step and reduce one variable. I'm going to do that either by solving for one variable and shoving it in the other or adding and subtracting side by side. So I'm going to subtract because I saw the two x's cancel. And this gives me negative y plus 2y is going to be y. This is going to give me 4z equals 12. And now I'm almost done with the problem. So the reason I want to reduce the number of variables is so that it's easier for me to find points. Now I need to just find any numbers whatsoever that work in here. I can think of lots of them. Here's one. If y is 0, then z has to be 3. If z is 0, then y has to be 12. And there's many others. I could keep going. If y, if z is 1, then y would be 8 because I'd subtract 4. If z is 2, then y would be 4. I could keep going and keep going, but I only need 2. So you just have to pick a couple values and then solve for the other. By getting it down to two variables, that works. But you'll notice something is missing. Where's the x? So how do we find the x? You plug it in. So at this point, you could rearrange, but I think I'm just going to go straight off of this. So if I plug in a 0 here and a 3 here, and you could also plug into the other one. In fact, it'd be good to plug into both. I get 2x minus 0 plus 24 equals 14. So somebody help me. What's x? 2x is negative 10. X is negative 5. And what I like in these questions is that's completely checkable, meaning you could plug it into both and verify that negative 503 works in both. My opinion is it's not too much more effort to find a second point. So let's find a second point. So I did 12, so let's do it. Now I'm going to go back and put in 12 and 0. And let's see what we get. We get 2x is 26, x is 13. I don't need more than 2 points, so I'm going to get rid of those. So this is my plan. Combine, step 1, find 2 points, done. What do I mean by done? So then how do you finish? You put one of your points here, either one, and tell me what these three numbers are based off of my points. 13 minus negative 5. So this is going to be what number goes right here? Yep, 18, 12, negative 3. Done. So that's my opinion for the fastest, most efficient use of your time. If you search online, you will find many other approaches to do this sort of problem. A lot of people like to do the cross product of the normals to find a direction vector. To me, this makes the most logical sense and is fairly short. But it does require that you combine and then pick a couple numbers. I picked this and this and solve for the others. So line of intersection, yes, it's a slightly bigger problem, but if you follow my advice, it's basically no longer than that. So that's another one of those topics I'd be like, okay, I think I've got that one. You can actually completely check your work. Now, this is only if you have time, but if you take your equation, it's kind of fun actually to check your work. If you had lots of time, like on a final or something, it's kind of interesting to see, is this on here? And fun thing happens is that when you put all that in, everything should cancel and you should just be left with 14. I think it does. 36t minus 12t plus 24. I don't know. I've come to find checking enjoyable. 14. It works. So if it's a line of intersection, it should work in both, and that would verify with 100% certainty that your answer is right. But it takes a little bit of time to do. Okay. I always liked things like that when I was a student because how many courses at UW can you know your answer's right before you leave the test? People tell me there's other reasons they don't like math tests, but I always liked that I could know a certain number of my answers were right before I left the exam room. Okay. Um, I felt like that wasn't true in a lot of my other classes. So there we go. There's line of intersection. Let's add that to our toolbox as we sort of do things of, okay, particularly line of intersection of two planes. Got it. I know what I'm going to do. So these are the sorts of things that, because the question was asked at the beginning, how do you recognize problems? Doing exactly what we're doing now. I would sort of be building the ones that seem like bigger, more monumental questions. And this is how you gain some confidence. Is that okay? Is this helping? I'm just talking to myself. Okay, good. Let's look at spring 2019. Um, I think the other question, there was a question about four, so explicitly asked. Is that person still here? So this is spring 2019 question four, just while I have this exam open. Spring 2019 question four. Okay, good. This has two different computational things and one somewhat conceptual thing. So let's play this game. So let's look at the whole page. Um, Move a few things around here. Make this a little bigger. Let's do with the first one. This is a one, I was trying to, I think this quarter, think of ways to ask this. Often it's hard to ask for a surface of motion because there's many correct answers. And what I mean by that is if I write x equals t cubed, y equals 3t squared, and z equals 6t, and I ask you to eliminate the parameter, there's not a clear one answer. There's many. Meaning you could solve for t and substitute this in here, and that would be one surface of motion, meaning this is a surface of motion. That's mostly kind of coming from 13.1 when we were trying to visualize, but you could have also plugged this in here, or you could combine these two. Okay, the question didn't actually ask you to do that. It asked you to check other people's work. So if the question is, how do I check other people's work? It's easier than we think. So the question was, do these work in here? So what you would do for this particular type of question, we're asking, if you do 18 times the x component, is it always the same as the y component times the z component? Let's check. So the x component is t cubed. That's this side. I'm just checking the first one first. Now let's put the y component, which is the 3t squared, and the z component, which is the 6t. Are these the same? Always. They are. And so that means that this is one of our, in my words, a surface of motion. If you were to visualize this, it's on this surface. That doesn't really help me because I don't really know what that surface looks like. But the question was just saying, does this work in here always? And the answer is yes. The two sides are always the same. But what does it mean by every point in the curve is also on the surface? So I'm trying to phrase this to, I would like to say, is this a surface of motion? But what I'm saying is, if you have, let me draw something. Here's a plane. Here's a curve. Okay, the way I've drawn this curve, it looks like every point on that curve is on the surface. Okay, here's another one. Here's a curve. Oops. The way I've drawn that one, it looks like some points are not on there and some points are on there. So I was worried when I wrote this question that some people might say, hey, there's a few times when it's on there. And when I'm saying the reason I wrote this statement was I was hoping to make it especially clear that I was asking for a surface of motion. Is every single point on here on these things? Meaning, if you plug this in here, is it true that both sides are always the same? And yes, in the first case, both sides are always the same. Okay, so let's check the next one. So the next one is it true that if you square the y and square the z and add them together, that you always get 1? Let's try it. Let's square the y, 3t squared, squared. Let's square the z, 6t squared. Does everything cancel, and is that always equal to 1? So my answer is no. It's not the same as 1. This is why I said every point, because someone might say, well, I can solve, and there is like 1t where it equals. That's not what we're trying to do. The other thing you could do is you could have just done the combining. So the answer is no. No. Yes. Okay. What about this one? Is it true that 12 times the y is the same as the z squared? Are those two functions the same? Yeah, they're 36t squared, 36t squared. Sorry, I dropped my pen. Coming back. Okay. So yes, they're both 36t squared. Is it true that when you take the y component and subtract the z component, it completely cancels? So y component minus z component. No, it does not cancel. No. Okay, so this was me trying to find a way to ask this question. I have in the past said, give me a surface of motion, but it's a little bit ambiguous for me to ask that. Um, okay, so this was trying to give us a chance to try to visualize. That's what that was. So if you ever saw that again, this is that idea of combining. Okay, the other questions are straight computation. So this, I actually, as a student, I like things like this because I immediately know what to do. So in my note sheet, I would have this new formula from today, R prime cross R double prime over R prime cubed. And then my advice from today was if they're giving you a value, plug it in as early as you can. but you can't plug it in. Occasionally, I've seen people do this where they plug in zero right away, and then they say R of zero is zero, 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 and then they say the derivative is zero, 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 and the second derivative is zero, zero, zero. That would be nice, but that completely loses the nature of the problem. You have to take the derivatives first, then you can plug in your numbers. C squared 6t6 R double prime. And I think this is just like the question from today. Maybe it's exactly the question from today. And then I want to plug in zero. So I'm plugging in zero. So I need the second derivative, the first derivative and second derivative at zero, and you do a cross product. Okay, so this takes a little bit of work, but let's do it. So if I plug in zero everywhere, I get 0, 0, 6, and I get 0, 6, 0, and I need the cross product. 0, 0, 6. This is the exact question from today. Uh, so this is 0 minus 36, I minus 0 minus 0, j plus 0 minus 0, k, negative 36, 0, 0. And then we're done if we can put it all together. So I need the length of the cross product, which we just found. That's this top part. And then I need the length of the first derivative cubed. That's it. So the curvature at 0 is 36 over 6 cubed, which is actually 1 over 6. So there's another one to kind of add to our toolbox of if it says curvature, I write down the form. I'm just going to put that up here. If it says 3D curvature, compute. Okay. So another one we've got, hopefully. Questions there, is that all right? And I think the arc length is also the one we did in class today. Where did I get the 6 in the denominator? So the length of this vector, so this is the magnitude of R prime of 0. Let me make it so I didn't scratch all this up. So the magnitude of that vector is the square root of 0 squared plus 0 squared plus 6 squared, which is the square root of 6 squared, which is 6. I knew that already, though, because it's just a vector 0, 0, 6. Yeah. So in the formula, these are magnitudes here. And so curvature will be a number. It's the rate at which the unit tangent is changing with respect to uh, arc length. So this one is fairly quick as well. The function is t cubed 3t squared 6t. I'm just copying this from above here. The arc length. So the biggest thing here is finding, or the thing you don't want to forget is finding the corresponding t's. But I think this is the exact example we did in class. So this is 0, this is 1. It's the integral from 0 to 1 of the square root of 3t squared squared plus 6t squared 6 squared dt. Then we compute. So there's another one at our disposal. And we did mention curvature in 2D. I think we saw that in that challenge question earlier. So we're building our little note sheet. Okay, we saw that today. We saw arc length. And facts like this are also on my review sheet, but okay. We got energy for a little more. So we kind of looked a bit. I didn't actually do a full tour of spring 19. What would we like to do next? So who's still here? What would you like to do? Or if was one of those your questions? I'm just pausing for a moment. Projections, spring 23. Okay. Let's do a couple things here. So first, we're going to spend a little bit of time here, and then we'll go look at the spring exam because you're spring 23. So let's do a little general chat here. Okay, so we're going to talk a few vector things. First off, so let's build a little collection. I don't know, 1, 2, 10, 0. There's a couple vectors. So we've learned a few things. Let's call this A. Let's call this B. So let's do a little recap of several vector facts, and then that'll lead right into projections. So first off, we know how to do A plus V. That's not very exciting. It's going to be 11, 2. We can visualize that. It's this vector that sticks out here. Looks like this. A plus B. Okay, that's not very exciting. That's not what your question was about. We could visualize the following vector, A minus B. And that's the vector A minus B. It's -9, 2. So go ahead on your little piece of paper if you're taking notes. Could you draw that? Here's A, here's B. There's many ways we can draw it, but if we do A minus B, it's this vector. It goes from here to there, A minus B. We also know how to rescale vectors. So yeah, all of this will, I promise, all tie in here. I'm just kind of saying a few things. What if I wanted to take the vector A and make it have length 7? So I would like you to rescale vector A to have length 7. So think for a second how you do that. Meaning I would like to give another vector that points this exact same way, except I want it to have length 7. And we will do projections, but this is actually one of the skills we'll need. If you multiply by 7, it makes it 7 times longer. So it makes it 714, and its length is the square root of 7 squared plus 14 squared, which is actually way bigger than 7. So this makes it 7 times longer. Yeah, so first you have to figure out its length. So the way you rescale a vector is you first make it a unit vector, which in this case it would be 1 over, let's see, what is the length of A? It's the square root of 1 squared plus, oh, it's the square root of 5. So it's the square root of 5, 1, 2. So that's just a reminder, this is the unit vector in the direction. Isn't it square root of 1 plus 2? I think there's some. Oh, okay, good. Okay. Unit vector in direction of A. And that you can actually check as a unit vector. It's not pretty, but if you did the magnitude of this, if you did this squared and added them together, you get 1. So that indeed is a unit vector. If you take that and multiply it times 7, it gives me a vector of length 7. And so if I put a 7 here, I have it. Okay, so I wanted to do that first because we're going to need that in just a moment. 7 times this is what I was asking for. That's how you rescale a vector to a given length. And that's kind of a useful little thing. Okay, questions on those pieces. So we can add vectors, we can subtract vectors. That's visually what that means. We can rescale vectors. Okay, those are things in our toolbox of skills here. And that works in 2 dimensions and it works in 3 dimensions. So let's kind of plop this there. All right. So then we have some other cool facts. I'm just going to list them over here. A dot B is the magnitude of A times the magnitude of B cosine of theta. A cross B is the magnitude of A times the magnitude of B sine of theta. We've learned that this is really good for finding the angle. So if I wanted to find this angle, we could do it. In fact, the dot product gives us a way to work around often having to find an angle. All right. So now we can do projections. So a projection question is another application of dot products. So let's come down here and let's play this game. And if we want to know a little bit of how, we can talk briefly. So the idea of a projection is you have 2 vectors that are tail to tail, and for some reason you want to go straight down from the head of this vector onto another. When we draw a picture like that, we say that A is projecting. I'm saying this carefully because a lot of people have asked me about this, is projecting onto B. A lot of people have been saying, how can you tell what is projecting onto what? The B is the ground. The B is where the 90-degree angle is. So if you look at it, this is the 90-degree angle. So the thing you're projecting onto is where the 90-degree angle is. It's the ground. Now, in this case, you can actually see the answer from the picture. What should the answer be? Even without, it's 1. If I have a vector that goes over 1 up 2, and it's this vector, and then I'm projecting it onto a vector that's on the x-axis, I already know the answer is 1. So I don't really need a formula. I started with an example where I already knew the answer. So the projection is 1. It's that length. Okay, so there's a formula for this. And the formula, just briefly, the formula is fairly quick to remember. You do the dot product, you divide by the thing you're projecting onto. Ultimately, the reason that's the case, if you're curious why, it's because the hypotenuse is the length of A, and this is the length we're trying to find. So if we called that x, you could say that tangent of theta is x over the length of A. And so x is the length of A cosine of theta, which is sitting right here. And if you get that by itself, you get the projection. So it's just commenting that contained in this information up here is a projection. So this is let's put this in words. This is the projection, component projection. of A onto B. All right, now let's do a whole bunch of examples of that. B is the ground, B is where the 90 degrees are. Let's go. And the projection is supposed to be something that makes your life easier when you leave this class. But I think that when it appears on exams, people get kind of flustered by it. So all you do is the dot product of these two things. And you get, in this case, it's going to be 1 times 10, which is 10, plus 2 times 0, which is 0. And then you divide by the thing you're projecting onto, the length of B, which in this case, the length of B is 10. And you get 10 over 10, which is 1. Ah, it matches up with what we expect. In fact, you start to notice that the length of B doesn't matter. So let's say we make B something else. Give me a number in the chat besides 10. 6. If you use a 6 here, how does the formula change? So now you're doing the dot product of 1, 2, and 6, 0. So you get 6 plus 0. But the length of B is 6. You get 6 over 6. It's still 1. So the ground vector doesn't really matter how long it is. It just matters that it describes the ground. I'll talk about that other part in just a second. Okay, so let's do a whole bunch of examples. Let's pretend we have a hillside that has a little bit of a slope. I don't know, maybe let's pretend it's 10 by 3. And let's pretend that we're pulling a wagon this way. And let's pretend that is 2 comma 5. Okay, a natural kind of physicsy question is how long is this? How much force is this way? So you could do a bunch of trig, or you can use a dot product. But we need a vector that points this way. So I'm going to use a vector for the ground of 10, 3. Okay, so let's call this vector 10, 3. And I'll draw them tail to tail so we don't add a confusion here. Okay, the moment you realize you're in a projection situation, it's very quick. You do the dot product. So the dot product is going to be 20 plus something. I'm going to leave a blank here. Divided by the length of what we're projecting onto. We're projecting onto this vector. What goes right here? What number's in this spot? 15. The dot product of these two things dividing by what you're projecting onto. So, like I said, it's supposed to be something that makes our life easier. This is 35 over the square root of 109. It's amazing how fast it can give you that. So let's play the game again. If I give you a few points here, let's pretend this is 1, 0, 2. Call this A. Let's pretend this is 7, 1, 5. And let's pretend this is 10, 4, 20. Can you find this length? So the moment you find yourself in a projection, you can say, well, if I could turn it into vectors, I can do it very quickly. So think about what that would be. So AB I can get. AB is 6, 1, 3. I did with subtractions. AC, which is the ground where the 90-degree angle is 9, 4, 18. And now I'm trying to do the projection of AB onto AC. So if I want that length, it's the dot product. So it's 54 plus 4. This is bad for me to make up numbers. 30 and 24. Oh, it's also 54. Divided by the length of what we're projecting onto. 9 squared plus 4 squared plus 18 squared. That's that length. So if you find yourself in a projection, that's pretty quick to compute. So dot products are, that's the primary use of dot products like in physics classes, is to quickly figure out how much of one vector points in another direction. Okay, so to the other questions. So now what part of what confuses people is the formulas. So what we've just been talking about, this has a funny name in the book. It's called the component projection of A onto B. So yes, you can put this in your note sheet. Is that a number or a vector? Tell me in the chat. It's a number. That's what we've been computing. Okay, so now let's finish the story, and I'll just make a new example, just so I'm trying to give lots of examples here. So let's grab another vector. How about 3, 4, just for fun. Let's grab another one here. Um, maybe I'll project the other way, just to make it seem scary. So let's do 5, 0. And I want to make this long enough so that it makes sense. 4, 6. Let's go this way. Okay, so first in the chat, I'd like to know what this length is. So tell me that length. It's a number. So you do the dot product divided by the length of what you're projecting onto. So I'm doing the dot product. So somebody's saying 20 over the square root of 52. We're projecting onto A, so it's going to be A dot B divided by the length of A this time. So it's going to be 20 plus 0 over the square root of 4 squared, which is 16, plus 6 squared, which is 36. So 20 over the square root of 52. Okay, I wanted to do enough examples so that we understood that's actually what I think of as projection. So the other question people have is, but there's another formula in the book. What's this other formula about? And it's on your note sheet too. Okay, so we're going to finish with that. Get rid of this just to clean up our page. So let's say you have this number. You now know the length of this is 20 over the square root of 52. Someone comes along and says, I didn't want that. I want the vector that points this way. Find me that vector. That's called the projection vector. I don't usually think about a formula for that. I basically ask the following question. I want to take A and rescale it to length, what was it? 20 over the square root of 52. How do we do that? How do you take a vector and rescale it to a different length? Now you know why I did this earlier. You make it a unit vector and you multiply by the desired length. So the answer to this is you take A, you make it a unit vector, and you multiply by the desired length. So I don't usually memorize this formula because I just memorized this one. I use it just enough that I know it. Plus, I kind of have a way to remember it because I'm projecting onto the ground. And then I just go, okay, if you want the vector, I will just rescale the ground vector. Now, an interesting thing is the magnitude of A is the square root of 52. because that's where we got that number. And the A vector is 4, 6. So when you see in the book, there's this formula that says the projection vector, what they're doing is they're taking this vector and they're rescaling. In this case, it would be B. They're making this a unit vector and rescaling, but this is the same number. The reason the formula sometimes looks funny is there's many ways to rewrite that. Like you could write the bottom as the magnitude of B squared in several other ways. So that's how I think about it. It's so it's easier to hold in my head. Sometimes it's useful to find that vector. Sometimes it's useful to get the point. Um, but I just think of it as one formula. I think of it as this formula. And then I think of the projection vector as a rescaling. Does that help anyone conceptually at all? The question might be about particular applications in the, yeah. The part that's like, if it wasn't for exams, the part that's practical is this. This is practical and useful. Um, yeah. And I think I have a video where I do like 20 projections in it called projections, projections, projections. I've made a few videos like this where it's just a whole bunch of projections in a row. I think maybe that's in the discussion board. Let's take a look. Yeah, somebody was asking about this. So I have a few different things if you want more. So this is what's helpful to me about the review. As you're reviewing, you're like, okay, that's something I need help with. I probably have a lot of stuff on it. So this is a review of what projections are. Am I showing this on the screen? Can you see this? The browser? Okay. So there's my cats. And then I have, this is my video, projections, projections, and more projections, where I do 10 minutes of only projections. And then more with the cats. Um, this is more than you need. Uh, but this is one of these topics that, when people are studying for the final, they want to review it as well. Um, I think there's just an uneasiness about a few of these things. Plus, we don't spend a lot of time on it in class. Okay, so that's one thing. And then there was Spring 23. I know you asked for hanging around. Let's look here. Spring 23, question 3B. Somebody's asked me that in the chat a few times. So let's finish with a little tour here. So here's spring, one final tour. Yeah, you can leave it with the fraction out in front, Ari. That's fine. Uh, we actually don't do the binormal or the unit normal in the homework anymore. I will talk about it as part of my 13.4 lecture. I'm kind of reordering how I do this. So it's more of an idea and less of an exam question anymore. Um, but you're for exam one, no, or exam two. Okay, so let's tour spring 23. So there's some naming of shapes. So it is good to put yourself, just say, what would I do? Would I be able to name this shape? This is fairly quick thing. So what's the name? You want to try to type it in the chat? We want to have a plan for this. There's basically 5 names to sort through. There's 2 types of paraboloids and essentially 3 types of hyperboloids. We don't want to be guessing. Um, so let's say a couple things here. I mean, I can review it all in a matter of moments. Why do I say this? Because this is basically all that can happen. X squared plus y squared, and then this doesn't matter if it's plus or minus, but let's say minus z equals 10. X squared minus y squared minus z equals 7. Those are the paraboloids. I threw in some random numbers, but I gave a way that you don't even have to think about that anymore. The way I gave was, what if you erase the x? What is that? And the words I'm looking for are either parabola, hyperbola, or ellipse. So what is this? Parabola, hyperbola, or ellipse? So if you eliminate the x, it's a parabola. If that's where the confusion is, that's fairly easy to deal with. Parabola means one of them is squared and the other is not. One squared, other not. Hyperbola is both squared. So if you had something like this, the 4 doesn't matter. It's a parabola. If you have something like this, it's hyperbola. If you have something like this, it's an ellipse. So when I look at this, if we haven't caught on to this yet, I cover up the x and I say um, parabola. The reason I know that is one of them is squared, the other not. So parabola, if you cover up x, comma, if you cover up y, if you cover up y, one of them is squared, the other is not. Parabola. The moment two of the traces are parabolas, we already know it's a paraboloid. That's what the oid means. It means two of the traces are parabolas. So this is a paraboloid. And then you look at the last trace. So this was minus 4y squared. Let's get rid of the z. What does that look like? Both are squared, and there's a minus between them. Hyperbola. So that's how you remember. You don't really have to like guess. You just cover up. I mean, if I was doing this, I would have just covered up x and said parabola, parabola, hyperbola, hyperbolic paraboloid. That's how fast I would have named it. This means that two of the traces are parabolas. This means the other trace is hyperbola. Okay, anyways, we could spend more time there, but that's the game. So this is something you would add to your notes of, oh, wait a second, one of them is not squared. Um, okay. The question was actually about 3B, but it's good as we start to pan through this just to see more things. Come on, browser. There we go. So when I look at this, I go, so now let's start hopefully accelerating. Area of the parallelogram, I'm thinking cross product. I'm thinking I want to do AB, AC, take their cross product, get its magnitude. At some point before I walk into the exam, I mean, that's something you need to get to a place where you can just read through an exam and already have a little bit of a plan for every problem. Find a vector that has length 5 and points in the direction of BD. Well, we were just talking about that. So you would find the vector BD, make it a unit vector, and multiply times 5. Okay, I have kind of a plan there. The line segment BE shown is perpendicular to AD. Find the segment AE. Yes, you could also do AB cross AD. Yes. There's something else we could talk about. There. Okay. This is a projection. What is being, so the question asks for this vector AE. I can tell you what I would do. I would immediately find the length and then I would rescale AD. So I would do AB I would find that vector. I would do AD. I would find that vector. And then I would do A dot B over the length of what I'm projecting onto. That would give me the length. And then I would rescale AD. In my mind, that's what I'm going to be doing to find AE. Anyways, that wasn't the question. Um, then there's a question. I've got notes on here because consider the line that contains the point and is orthogonal to this plane. Find 2 points of intersection of this line with the paraboloid. So this question is about a line. I need a point. I need a direction. I need to start filling things in. So that's what I've been trying to give you in class is this plan. They gave me a point. It's orthogonal to this other plane. It's a lot to read through, but this is one of our happy situations. This is the line we want. This is the plane they gave me. This is pretty nice. Hey, that points the correct way. So this is one of these questions where they gave us everything we needed. And then we'll finish with this intersection. The question wasn't about this. I'm just touring through the exam. Find the equation of the plane. And now I need a point and a normal. It contains the intersection of these two planes. Hey, wait a second. Intersection of two planes. That's in my wheelhouse. Intersection of two planes, I have a strategy. 2 points. So back to that question. Yes, this is a convoluted problem, but I have a plan already going into the test. So this is just how I think about test taking. I don't know if this is helping, but I would immediately try to find 2 points by combining and then finding 2 points. Anyways, uh, that's where I'm trying to put things together. You're trying to, as you study, say, okay, this is kind of like that other question I did. Now I have a plan. You're trying to build as you study. I think some people study and they're like, okay, here's another thing I don't know. Here's something else to make me sad. You don't want to study that way. You want to start putting ideas together. Um, Angle of intersection, hopefully that's in our wheelhouse of things we know how to do. Okay. Curve, that was your question. Oh, your question was 3B, is that right? Or was it 4? Remind me, Ria, sorry. Say, I never know if you're going to get there. You're talking forever. Okay. 3B. Apologies for writing. Is that this one? Am I on the right one? Great. This question actually is the thing we just were seeing kind of in lecture today. Yeah. Thanks for being here, Yanka. So this is spring 23. Let C be the curve of intersection of these two surfaces. Parameterize this curve, then use the parameterization to give the arc length. So this is particular to 13.3. The question will end with arc length. Meaning it will end with finding 5 things. You'll have to fill in these 5 spots. One, two, three, 4, 5. But this is sort of a practical issue of in order to compute anything on this intersection, we need some equations. And so the challenge in this problem is to parameterize, is to come up with 3 formulas, whatever they are. I wouldn't write this f of t. I'm just writing this for effect. Your job is to figure out what goes here, what goes here, what goes here. What are those 3 formulas? And the rules are as follows. Whatever formulas you use, it has to be true that the y formula is 1/2 of the x formula squared. That's one rule. I'm getting that because it has to be on this surface because it's on the intersection of both these. The other rule is that z has to be 1/3 of x times y. There are many ways to parameterize this, but usually if there isn't a circle, typically we just pick one of these three to be t. But as we discussed in class on the similar problem, you would like to choose something where you can solve for the other variables. If we were going to do a lot of this, I would talk about sort of building a tree of our variables. When I look at this, I see that if I choose x, I can get y. And if I get x and y, I can get z. So if we were going to do a lot of this, I would talk about how to think through. But basically, you can see that everything can be obtained from x, can be immediately solved for from x. That suggests that maybe this would be a good choice. But you can pick it to be something else. I mean, you could make this be something crazy. You could have this be t plus sine of t plus e to the t. But the more complicated you make this, the more complicated the derivatives are going to be. And so we tend to want to make it as simple as we can and still meet our conditions. So usually we just pick t. Then the moment you make this choice, y has to be 1/2 t squared. And the moment you make that choice, this is t, this is 1/2 t squared. You can simplify that. So you can say that z is 1/3 times t. So it's 1/6 t cubed. Okay, that is what we call a parameterization of the curve. So that's what this was talking about. Not the only answer, but probably the simplest answer for parameterizing. That was really what the question was about. The arc length part is somewhat quicker. You're going to take the derivatives. So there's going to be a 1 here, the derivative of x. There's going to be the derivative of y here. And there's going to be the derivative of z here. So let's see, a 3 comes down, so it's going to be 1/2 t squared. And then based off of the choices we made, we need to figure out the corresponding t for this and for this. So what are our bounds? Yep, 0 to 3. How did I get x prime? So x prime is the derivative of this. So the derivative of t is 1. The derivative of this is 1/2 times 2t. And the derivative of this is 1/6 times 3t squared. But what you're starting to see is that when we want to measure things along a curve in 3D, we basically want to just describe the curve. The challenge in 3D becomes how do we describe a certain curve or how do we describe a certain region? And you actually have a lot of flexibility to do it, but sometimes there's like easier choices. Without describing the curve, without getting it down to one variable, we can't plug it into formulas. And so the challenge is really how do we reduce the information they gave us to one variable? Yes. Yep. So we're trying to meet the condition of whatever I write down works in both of these. Yeah. The last part of the, so, if I was grading this question, this is most of the credit is did they parameterize? Did they put things in the right spot? This particular exam, I asked someone to compute. So there is a separate task, which is unrelated to the main point, maybe worth a point here. But there must be a reason I asked the students to compute, like this must simplify, or I couldn't have asked this. So let's take a look. So again, this is one of these where at first glance it doesn't look like it simplifies, but there's no way I could have asked this if it didn't. So I'm going to hope that it's a perfect square. So in my head, I'm thinking, if this isn't a perfect square, I'm in trouble. But if it's a perfect square, then this has to be 1, and this has to be 1/2 t squared. And the middle term comes out right. So it's 1 plus 1/2 t squared. And then the squares and the square root cancel, and we have it. So it's 3 plus 3 cubed over 6. One of those threes cancels. So 9 over 2, 3 plus 9 over 2. The bounds came from figuring out, and this happens even in problems where they already give the parameterization or they give a curve. If someone gives you a point, that's giving you X, Y, and Z. So they're telling you this is 0 and this is 0. And a problem like this, and this isn't just a problem, it's in general, if they tell you X, Y, Z, the problem assumes that you know from that you can figure out what T is. So the question is, what T makes all three of those true? It's T equals 0. So when I do a problem like this, I always want to immediately write what's the corresponding T. Similarly, for the other one, when this is 3 and this is 9/2 and this is 9/2, and we could check their work. Like whoever wrote this question it needs to work out. So if T is 3, does this give me 9/2? Yep. Does that give me? That's it. Um, okay. So I feel like we hit arc length. We did a tiny bit. I'm just kind of characterizing where we're at and what didn't get covered here. We talked a bit about several of these things. We did hit that a bit. We've done a little bit of this and a tiny bit of this. We did eliminate the parameter. We did the intersection of two surfaces. And we did arc length. So we've seen a little bit of almost everything. So I do this sort of checklist of like, if I was a student, have I missed any major topics? I think tonight we've hit almost all the topics. And so now we can flip through a lot more exams and see like, what am I missing? What's confusing me? All right, I think we'll call it there. Thank you for coming. And ask lots of questions in quiz section tomorrow. And then we will continue reviewing on the discussion board tomorrow and in class on Wednesday. All right, have a good night. Lovely, lovely. Let's see here. Stop share. Let's close it out.